Section 4.6 is change of bases. So we talked about uh, basis coordinates for a given vector relative to another basis. And now if we're in two general bases, say in our first example here, we have a basis B1 and B2, and then a basis C containing vectors C1 and C2, each of which is a basis for a vector space V. Our question now is to see what, to change from one coordinate basis to another, right? So to represent a point or an element or a vector in the vector space V, to take a representation in terms of B coordinates and rewrite it in terms of C coordinates. Okay, so this first example gives us a kind of an easy setup for the problem, and we'll extend that into more general types of questions or transformations in a moment. So suppose we have that B1 is given by this linear combination of vectors C1 and C2 in the other basis. So our basis vector in this set B1 we can form as a linear combination of C1 and C2 as follows. Similarly, B2 has a linear combination of C1 and C2 in order to form it. And what they're really asking us to do here is they say, okay, say we have a vector that's given by this linear combination of B1 and B2. 3, -1 is its coordinate, as its B coordinate vector. Okay, or its B coordinates is a way to think about it. So remember that the weights in this linear combination of the basis vectors is what makes up the coordinates of that vector under that coordinate basis. So now the question is, they want us to find this vector x in the C coordinate basis, or the C basis coordinates. So we need to translate from B coordinates to C coordinates, and we know our B coordinates as follows. Well, this actually kind of follows somewhat straightforward. It's almost algebraic when we look at this. 3B1, we want to write x in terms of linear combinations of C1 and C2, right? So remember that here's a statement for that over here. It's the values V1, V2, such that they're the weights against the C1, C2 basis vectors. Okay, so that's what we're looking for. Well, in other words, we're looking for a linear combination of the vectors C1 and C2 that represents x. And this really just turns out to be a straightforward substitution, right? We have this as our given B coordinate vector for x, or x in terms of B coordinates. So if we write it down in its algebraic or its linear combination form, 3B1 minus B2, then we substitute for B1 here and then B2 here, combine like terms, and we'll have an expression in terms of C1 and C2. When we combine this, we come out to just 10C1 plus 0C2. And those weights, the 10 here and the 0 in front of C2, give us the coordinates in C. So those are our C coordinates for the vector x. So this one was easy because we're given these relations. So it's kind of an intermediate way of seeing how to do this. You might be able to come up with those on your own. We'll see a method that actually essentially implicitly establishes these relationships, but we don't actually need them if we're going to change from one basis to another if we're given different information. So we'll see what that different information might be. So one nice theorem for this, and it's essentially reaffirming what we've already known. So this is, again, still for the same type of problem we just looked at. We're given two bases, B and C, and they're both a basis for a vector space V, or they're each a basis for a vector space V. There's a unique n by n matrix, so that's good to know. This is what I was hinting at previously, such that we can write, or we can get the vector in C coordinates for x by a transformation, this n by n matrix, in other words, this matrix times the B coordinates of the vector x. So this is a transformation from B coordinates to C coordinates, as we see here. And that's what then the indication here is showing us, B to C. The arrow's backwards because the problem's a bit of an inverse looking problem, right? We're really looking for the coefficients of linear combinations of X that form X's coordinates in C. And that's really just the solution to this AX on this side equals B on the left side matrix equation. So the columns of this P, C to B, or B to C transformation are the C coordinate vectors of the vectors in the basis B. Okay, so they are the representation of the B1, the B basis vectors in terms of C coordinates. And that's exactly what this notation is telling us here. So in order to form this transformation matrix, we form each of these vectors. Well, we already know what each of these is. We know that B1 had on the previous page, in the previous example, we're going to look down here, right? And again, we'll call this P from B to C, the change of coordinate matrix from B to C, as this indicates. We looked at the previous example, and I'm thinking about what these columns are. Right? Well, I know that B1 and C coordinates on my previous example. Well, 4 and 1 are my weights. So that's going to be my first column, 4 and 1 here, right? That came from this. To form my matrix, my change of coordinate matrix from B to C. It acts on a vector in B. Right? Anyway, this is given here. And then my second B2 coordinates in C coordinates, or my B2 vector in C coordinates, is given by, this is the same relation that was given initially here. So we know B2 as a linear combination of the C basis vectors, and that makes up this column. And that's a pretty easy way to put a matrix together. We just pull the coefficients from these algebraic equations and form the columns in this transformation matrix. And remember, when we multiply this matrix times this vector, this 3, -1, we change our B vector into a C coordinate vector. And we see that that's exactly what we had, 3, -1, what we started with, and we ended with 10, 0, going from B coordinates here to C coordinates in the end. So that is, that's our technique for doing so. And in this case, this was a bit backwards. We had more of a linear system in this case, or at least just a substitution of items in this one, in which we then could parse out or factor out what constant is times each of our C basis vectors and form that as our C coordinate vector. So that this formalizes the rule, and moreover gives us a transformation matrix that we might be able to use. And we see that this transformation matrix is doing exactly what we thought. If we multiply this by this vector, this B vector, we get a C vector. So that's its coordinate represent. This is the B coordinate vector. We can represent it as a C coordinate vector, and they're essentially the same vector, but for different bases. So a more general example, and this is really like basically the main example or the main problem or question in this section, and it's really our last example, is if we're given vectors B1, B2, and then C1, C2, and then we're told that they're bases for R2, and they should be bases for R2, so we want them to definitely be that to be the case for this to work. They'll ask us to find the change of coordinate matrix from B to C. Okay, so we'll remember how this goes, right? This is, if we're given a B vector, what we're looking for, maybe B1 we'll say, which is right here, what we're looking for is the weights, the linear combination, so x1 times this plus x2 times this. Well, here's the coefficients of x1 and the coefficients of x2 in a linear system, and they need to be equal to this B1 vector. Okay, so I'm trying to figure out what the weights are. I'm trying to figure out what the C coordinates for this vector is. So I'm trying to solve for the weights in this linear combination. So this is my linear system to do so, right? Or my augmented matrix for the linear system in order to do this. So I'll take this all the way to reduced echelon form just to solve completely for each variable nice and cleanly. And I have that my first coordinate, my first weight should be a 6, and my second weight should be a -5. and that's to represent B1 in C coordinates. Okay, so there we have it. And what we've used is the fact that our change of coordinate matrix from B to C is, well, it's these columns of C vectors. So doing the same for B2, then we'll write again, what we're looking for is x1 times C1 plus x2 times C2 is equal to this vector. So I'm trying to solve that system. Well, the x1 coefficients are here, and the x2 coefficients are here, and that's equal to the right-hand side here. So there's that same augmented matrix. Notice this is the same as the previous part of the problem. And well, I take this to reduced echelon form. A few steps in between here will get us to what we've got here. And we see that, well, our first weight should be a 4, our second weight should be a -3, and that makes up the coefficients of the coordinates, the C coordinates of our B2 vector. Now, if I write these two things together, remember that B1C and B2C form the columns of the transformation matrix from B to C, B coordinates to C coordinates. So I write these two as columns, 1 and 2, and that's coming from the previous theorem. So now I can form that transformation matrix just as well. I use this step right here. B1C coordinate and B2C coordinates make up my columns in this 2 by 2 matrix. And then we arrive at that transformation matrix. Now, the second, we're asked to find the change of coordinates from C to B. We're going to go the other way. Now, this is it's a little bit, like I said, it's happening more or less as an inverse in some sense, right? We're looking for the weights, the x1, x2, the solutions to this equation, this matrix equation here, that give us this this B vector, right? In order to find the representation of B in terms of C coordinates. Okay, now going the other way, it's essentially just the flip of this. We're looking for the weight such that C1 is equal to x1 times B1 plus x2 times B2. So our coefficients are now, if we think about it as a linear system, our coefficient columns are these. x1 and x2 are times this. So I form this matrix. And if I'm trying to find C1's representation, the weights for B1 and B2 that will give me C1, well, then I put C1 as my right-hand side. Well, I'll have the same coefficients if I'm looking for C2, only my right-hand side will be different. So I set up the same thing. The vectors B1 and B2 are written into this coefficient portion of the matrix, and then my right-hand side is the C vector I'm trying to represent in B coordinates. Well, I'm going to put both of these matrices in row echelon form or reduced echelon form. Notice the same coefficient matrix. That'll always be the case. So why don't I just do it all together in one step? You know, after all, we did something similar up here, had to follow the same steps for each of these to get them into reduced echelon. So we can put them together as this augmented matrix. Right, so I've got our same coefficients on the left, and then on the right, I just put each of my C vectors, C1 and C2 as their own columns, and I'll put all of this into reduced echelon form. And when I have reduced echelon form on the left, I can pull both of my columns, my new vectors, my B coordinate representation of my C1 vector and my B coordinate representation of my C2 vector, and write them. I could write those vectors down as that, but what we're looking for is the transformation. And remember that transformation is exactly that. And maybe to give it some notation, I'm saying it, but I haven't done it. But we have, this is C1 in B coordinates. And this one is C2 in B coordinates. It's just backwards from everything written in the previous theorem, but we can go this way as well. We can go from one basis to another. I'd recommend going in the forward direction for a while when you're first using this theorem, so that way the notation is clear and the algorithm is easy to follow. But once you get the hang of it, you realize working in either direction from one basis to another, you can perform the same things. Now, how do we know that we're going to have a reduced row echelon form here? That's because we're always going to be dealing with bases, right? This is always going to be a basis, whether or not they're the B1, B2 basis vectors or C1, C2, or maybe we go from B1 to Bn and C1 to Cn. It's always going to form a basis, so it's always going to have a full rank reduced row echelon form. We'll have a pivot position in every column in its reduced echelon form, i.e. we'll have the identity matrix in every one of these reduced forms, thanks to the fact that these are bases. So we'll always have full solutions. We'll always have a transformation matrix from one basis to another, and that almost is a sketch of a lemma for the situation. So what that essentially tells us is that if we're given any basis for R2 and then any other basis for R2, we can come up with a transformation from one basis to the other. So when one of those bases is the standard basis, we did this previously in section 4.5 at the beginning. It was a quick coverage of a small part of 4.4 that we didn't do a full coverage on. And that was a much easier transformation to come up with. In this case, we generalized it. So that's really all that's happened. But if you follow these steps, and you can do it either way for finding these transformation matrices or the change of coordinate matrices, then you'll be able to at least first perform this and get the answers we're looking for. But with some practice, I think you'll start to understand what it is you're actually doing. What you might want to do as an exercise is leave these two basis vectors, B1 and B2, and then find the transfer or the change of coordinate matrix from these two basis vectors to the standard basis vectors. So instead of using C1, use E1, 1, 0, and C2, 0, 1, and just see how that goes and see what you come up with there. And you should see something that is consistent with what we've done in the past. So that's change of basis. That's really all there is to it. We'll see a little bit of change of basis later on in the course, so I wanted to make sure we had this basic skill covered. But otherwise, this is all we really need from this section.